Good morning and welcome you all to this session on conduction and convection heat transfer. Now, in this session, we will start a new topic, extended surfaces and fins. You have seen in several cases, practical scenario, we use an extended surface. For example, in a wall, hot wall, if you have to enhance the heat transfer, we add some extended surfaces. You will see in many places the radiators of a car. In heat exchangers, if you see, the two fluids exchange heat between each other. One is hot, another is cold, and they pass through different passages. One is, for example, in a shell and tube heat exchanger on the inside tube, another is the outside annular area. And you often see that to enhance the heat transfer, there are extended surfaces attached to the inside tube to enhance the heat transfer there. So, several applications are there. In buildings, you will see the fins are there to enhance the rate of heat transfer at the outside wall. Now, the basic principle of using extended surfaces, which are known as fins, to enhance the heat transfer depends upon again the Fourier law. Whole lifetime, the entire study of heat transfer, I tell you, those of you who may make career in heat transfer will remember this, depend that the pivotal point is the Fourier heat conduction law, which is used in convection heat transfer also, that is heat flux, total heat transfer rate is K thermal conductivity times the area times the temperature gradient. So, we can increase the heat transfer rate by increasing the thermal conductivity of the fluid or the solid. That is a property. We can increase the heat transfer rate again by increasing the area, that is the geometry. More is the area, more is the heat transfer. You know that when you want to cool hot tea, sometimes we pour it on a flat plate where it gets more surface area, cold, being rate of heat transfer is enhanced. The third one is the dTdx or dTdr, temperature gradient. Now, one is the property, another is the geometry, and dTdr is the temperature gradient. That depends upon the boundary condition and geometry for conduction. And for convection heat transfer, this dTdr depends upon the flow condition, which will be dealt in more details in the convection class. And the example of that is, again, first we pour the tea on the plate, but still we are not satisfied, then we try to blow air over it or put it in the bottom of a fan. That means in that case, we create a higher temperature gradient. We don't touch area, we don't touch the property. What do we touch? Change the flow field, as I explained earlier, temperature gradient. So, therefore, in heat transfer, this has to be remembered for whole life, that these three parameters, scientists are searching that these three parameters have to be dealt with to change the heat transfer rate. Now, in extended surface or fins are used to increase the heat transfer rate by increasing more surface area. How it is done? Let us consider a wall. This surface of the wall, we are not interested what happens this side of the wall. Just I have drawn the figure for your understanding. The problem is posed that this is the outer surface of the wall, this surface, which is kept at a temperature Tb. The nomenclature B is used, that is base temperature. That means from this wall, and this wall is exposed to an ambient T infinity. It is a hot wall. This may be considered that something is generated here in terms of energy. It may be the outer wall of a building where too much energy is generated because of some action. Huge people are there making noise, making some functions and all these things, so that this becomes hot, or it may be the wall of a furnace where the energy is generated. These are the practical examples that we get a hot exposed wall, this surface of the wall at some high temperature Tb, which is greater than T infinity. Now immediately one person will tell, okay, then you have a heat transfer Q. I tell you, it is H if you prescribe H as heat transfer coefficient, which is again a very complicated thing. You will see how complicated it is, but it's the fun when we will deal with convection. But at present we are happy that H is given as a parameter which is constant. Then people will tell, if A is your surface area of this wall, then fine, you have this heat transfer. Are you happy? No. I am not satisfied with this heat transfer rate. But H is fixed. I cannot change. The flow field is such of the outside air I cannot do. So what you can do? I cannot change the T infinity, this is ambient temperature. Then I have to set another refrigerant or air conditioning plant to reduce the temperature. So this you have to accept. Okay, I will enhance the heat transfer rate by enhancing my area. How? Wall is fixed. How you will increase the area? How can I increase the outer wall area? So what I do? I add a additional surface like this in a plane geometry for simple understanding. Now let us consider this part of the wall. I attach a rectangular surface like this, a three-dimensional view. My drawing is not that good. I think you can understand it. So I add this surface with a high thermal conductivity. It is not insulating material. It is a thermal conductivity high. K. Let K is the thermal conductivity, which is very important of this. Now what happens actually by adding this? If I tell that it provides additional area for heat transfer, it is understood. How? Now when heat is flowing from this area, now this unexposed area remains same. They behave as the same thing, H into A Tb minus T infinity, where A is this area plus this area. So this area, let us now consider H. It is very important. I am telling you, few books I don't know explain this way. They simply write by providing more surface area. But how you have to understand surface area is being provided? At the cost of what we are providing the surface area? You, please come to the first bench. You. Hello. You. Yes. You're next to you. You. Yes. Hello. You. Yes. Come and sit here. Not you, in front of you. Yes. Come and sit here, please. So now, a thermal conductivity K. Now what happens if this is the height H, and if I consider this width for understanding is our B, then from this part we have a heat transfer Tb minus T infinity, H into B into Tb minus T infinity. Try to understand this. This is very important. I tell you, for the first part of the deductions this may not be important, but to understand the field efficiency it is very important. Now you can tell, sir, I am generating the same area H into B here. So why you are bothered so much? I am generating the same area, but you are adding materials, that means a thermal resistance. What does it do? That this exposed area HB is not at a temperature Tb, because there is a temperature drop. That's why we tell this is a thermal resistance, that if you add more material and take the surface area somewhere here in the direction of heat flow, means the temperature drop is there, until and unless thermal conductivity is infinity. Less is the thermal conductivity, more is the temperature drop. This way we realize that there is a reduction in the heat transfer rate. That means adding this material reduces the heat loss from this part of the pipe, a surface where it is attached, but doesn't matter. Each and every portion the heat is being transmitted in this direction, in this direction. Why? This is because we have a temperature gradient from Tb to T infinity. So each portion, at each length, if we consider this as the distance x, and let this be the length of this, from here actually, this length, this is an isometric view, this length L. So along the length you have a temperature drop from Tb to some temperature here, but this is relatively higher but lower than Tb. So at each and every point, even if the temperature is lower than the base temperature, but it exchanges heat to the surrounding because of the huge surface area. Let us consider a section here at a distance x. I draw a simple two-dimensional surface like this, then it will be easier for us to understand that. Let us consider at a distance x, we take an element of length del x, and heat is conducted from the base, which is at a temperature Tb. From here it is conducted at this position, let Qx is the heat coming in. Then there is heat transfer through the surfaces of this element, and rest part of the heat is being conducted. That means this heat transfer through these lateral surfaces is huge. Because of this, it draws more heat here. Finally, it is connected to here. That means from the base, it draws more heat. That means, what are those lateral surfaces? That means this one. I draw it here. This del x, you can understand this like this. That means I think you can see it. That means these lateral surfaces, one is the top surface, another is the bottom surface. That means del x into B, top and bottom. Then this surface, that del x into H, del x into H. So you see there are four surfaces from which it transfers heat by convection. Here, if you cannot guess it from this three-dimensional drawing, that this surface, top and the bottom, that means one is this top surface perpendicular to this direction, that means this top surface, this one, that is B times delta x. Similarly, the bottom one, B times delta x from the bottom surface, delta x and width in this direction, perpendicular to the plane of the board. And also this surface, that is this one, whose H into delta x, this area, and the rear one, that means it has this open or exposed surface to the ambient, which transfers heat, and it has some temperature T at distance x, which is less than Tb because of the thermal conductivity of this material. That I accept, it is not at Tb, but even at that less temperature, it has huge area to transfer a huge amount of heat. and this way it is added up for the entire fin, so that it helps to draw more heat from the base than that was being transferred without the attachment of this extended surface, which is known as fin. This is a rectangular fin. Clear to everybody that how then the fin works, that it puts an additional thermal resistance in conduction along the direction of flow, but it gives huge heat transfer by convection by allowing a lateral, more lateral surface, which are even less, being even less than the base temperature, but transfers a huge amount of it because of huge surface area. So now, if this be the problem which we have understood, then next part becomes so simple that why not we then find out the conservation of energy principle, no thermal energy generation. One rectangular fin if you consider, let this is Q convection from the lateral surfaces. Then Q X which is coming is distributed as Q convection plus Q X plus del X. Clear? Now Qx is minus K Ax dt dx. What is Ax? Ax is the surface area here. Here you can say that it is uniform, but I take a variable area. Let us consider a variable area. Let us consider a variable area. I have shown you here a area which is straight, but we can consider a variable area now for general purpose, but ultimately we will be solving this. This is a variable area. This is a variable area. Okay. So this is Qx, this is Ax at a distance x, then this is Qx plus del x, and here this is del x. Very simple. Here Ax is a function of x. I am not writing Ax plus del x, not necessary. Then Q convection, that is the heat rate transfer. So that's why minus Kx dt dx. Now if you solve this by expanding Taylor series and take it here, then Qx plus del x is Qx plus del ddx of Qx dx. That means minus K take all sorts of Qx plus Q ddx of Qx del x plus Q convection What is Q convection? Now Q convection can be written like this. We can now rub this one. We will go by that. Now Q convection can be expressed as this. If you define a perimeter P, for example, here you can understand better the perimeter in this case is the perimeter of this surface. That means here P plus H plus B plus H, 2B plus H. So therefore, if you consider P as the perimeter of this lateral surface, which is perpendicular to the plane of the board, then Q convection can be written as area H times the area becomes the perimeter into delta x. In terms of perimeter, it is perimeter into delta x into T minus, T is the temperature there. At that location x, T is the temperature. So in terms of the nomenclature perimeter, I can write this equation as Hp delta x T minus T infinity. So therefore, I can write the equations in this fashion, that ddx of Kax dt dx minus H into P delta x. You are very, very good. Delta x, I am sorry, there will be delta x. So Hp into T minus T infinity. Very good, there should be delta x. Yes, because this is Qx plus del x is Qx plus ddx of Qx into delta x, neglecting the higher order terms. Very good. So that delta x gets cancelled. Now this is the temperature distribution equation. Difference is that here heat is transferred simultaneously for each and every element, both by conduction and conduction through lateral surfaces, which so far we did not consider. So that means it precisely boils down to a conduction problem, where lateral surfaces at each and every section of the conducting material along the length of the heat flow shares in the convective heat transfer. Okay, that is the only difference. So therefore, if we know the physics, then we can find out the basic governing differential equation. For the temperature distribution, let us consider a very simple case: constant thermal conductivity, no temperature dependence, and this type of rectangular fin. That means A is constant. Then we get a very simple equation, d square T dx square minus Hp by Ka T minus T infinity is 0. Okay? Now if we write by transforming the variable, dependent variable temperature, as in the form of excess temperature, that means I change the temperature variable T transformation, T minus T infinity as theta as the variable. That means it is the temperature over the ambient temperature. Then dt dx is d theta dx, d square T dx square is d square theta dx square. But the advantage is there, here only we get theta. That means this looks like a simple school level problem, that d square, by defining this and by defining m as root over Hp by Ka. M is a parameter which is just defined by root over Hp by Ka. Hp by Ka is the m. Okay, if you define m as root over Hp by Ka, then we get an expression d square theta dx square minus m square theta equal to 0. If we define m as a dimensional parameter, then we get an expression d square theta dx square minus m square theta 0, whose solution is very simple. Now we define this as square root, or rather m square is Hp by K. This is because Hp, K all are positive. Okay, so m is a real quantity. That means Hp by K can be expressed as a square of a real number, m square. M is a real number because Hp, K cannot become negative. That's the logic. Otherwise we cannot define just square root of something as a real number, you have to investigate whether this is positive or not. So if we do so, rest part, the solution of this complementary function, you find out there is no particular integral, that side is 0. This is a second order differential equation. It is an exponential solution. E to the power mx plus c2 e to the power minus mx. Hyperbolic functions. C1 exponential function, whatever you call, e to the power mx. That's all. Now the boundary conditions. Okay. Now the boundary conditions. What are the boundary conditions? Tell me. Now boundary conditions, then you ask me, sir, how do I know? The governing differential equation comes from the principle of conservation of energy, or anywhere principles of conservation principles, and the boundary conditions come from the physical problem defined with its boundary and other conditions. That means the boundary conditions have to be physically defined. One boundary condition that is defined or prescribed by the physics is that base temperature is Tb, where from x is measured. So therefore at x is equal to 0, T is equal to Tb, which means theta is equal to theta b. Theta b means Tb minus T infinity. That means theta, in terms of theta, it is theta b. What is another boundary condition? For another boundary condition, you have to search for another boundary condition with respect to x. That means you have to find out what is the boundary condition at x is equal to L, if L is the length of the fin. So you have to know whether it is insulated or something.